Hey, we're back. Oh boy, this is an amateur radio extra class. My name is Gary, ham radio call sign Whiskey 4 Echo Echo Yankee. And the thing I'm so excited about is that on Tuesday nights, we're 3 weeks behind because we had Hurricane Helene come in, and then we had follow-up internet problems that just knocked us off the air. But we're back. Credit to Charter Spectrum. They got our connection back up to speed. YouTube live stream is rolling right now with 33 watching us over there. And we have our Zoom classroom with 13 participants in that classroom at the moment, but more to come. And it's so good to be here, and we really appreciate you. I mentioned it's a ham radio class, the extra class. We work out of this book. It's the American Radio Relay League License Manual for the extra class, the 13th edition. This is the one you want because this has the new question pool. And what we try to do is go through the book chapter by chapter, sometimes dividing a chapter in half so that we can get toward the end. And if you have your ham radio general class license right now and are ready to upgrade to the extra class, we'll get you prepared for a 50-question multiple choice test and get you going. So we've had to reschedule, move things around a little bit. Bruce, if you take the laptop, and it's kind of small here, it's kind of hard to see, but the top on 1029, that's us. We're going to do chapter 5 tonight. Did I see chapter 6? Chapter 5. We're actually going to take a Christmas break. Our last class in December will be December 17th, where we'll have part 2 of antennas and feed lines. Then we'll come back in January and complete chapters 10, 11, and practice tests. That arrow there is the Christmas break, where it will be 2 weeks off for Christmas. But I think you'll enjoy that, we'll enjoy that. Don't tell anybody, but we're going to have a general class and a technician class starting in February now. That's the plan. So, shh. Don't tell anybody. But if you did tell anybody, they can email me and I can get them on the list for the class. So it has been an eventful weekend. This was the CQ Worldwide DX contest. Bruce was in it. I don't have his scores, but he had a great time and there worked some nice DX. Dave and I were also in it. Dave, we have your scores up here on the laptop right now. Bruce, if you want to take that, and then Dave, maybe you can tell us a little bit about your experience. We'll come back to you here in a second.
Okay, yeah. I'm mostly a CW guy, so when it comes to a sideband contest, my intent was just to play in it. I wound up being in it for 5 hours. It was so much fun. It was a blast. And I think it's been commented already that 10 meters was just wide open. I've never seen 10 meters so crazy. And I'm just running 100 watts into wire antennas. So I wasn't, I was probably getting a 20 to 30% response rate doing search and pounce, but it was so much fun I just didn't want to stop. So this was my first effort at this contest, and for that I feel very, very good about what I did. Wait till you see Gary's scores though.
Yeah, it was a huge amount of fun. So you put 5 hours in the chair?
Yeah.
I put 25 hours in the chair. And last year I actually put 21, so it's about the same. But I am proud to say that I crossed the 1 million point barrier. I had 950 contacts. You can see there the breakdown by bands, and just a little over 1 million points. And actually the last hour and a half of the contest I stopped because it was just getting to be too much. But this is the best I have ever done. It's entirely the result of propagation. Propagation on the high bands, 10 meters especially, was just outstanding. So I'm very proud of what I was able to accomplish here. It's an all-time record for me, and it was just a huge amount of fun. So I really encourage you to investigate contesting. A little bit of masochism in there gives you, a little ringing in the ears sometimes, but it can be a lot of fun. Come back to me just for a second there, Bruce. Our friend, who actually used to switch where Bruce is doing right now, our friend Matt Crom, stateside call NU4E, who lives over in Piedmont, South Carolina, a good friend of ours. He is world class. And I think he's #1 in the United States and #1 in North America with over 7 million points as an individual operator. Hats off to you, Matt. You did a great job. All right, let's get going. But before, we want to point out that coming up this weekend in Lawrenceville, Georgia, is the Stone Mountain Ham Fest. And it's also the ARRL State Convention for Georgia. Dave and Vicki are going to be there. Bruce and I are going to be driving over. And so we'll be there on Saturday. Both of us will be on that on Saturday only. If you'd like to come on over and say hello, if you're going to be in the area, we'd love to see you, shake your hand, and talk about what's going on. And a good time will be had by all, I am sure. Stone Mountain Ham Fest. This will be the first time I've gone to this one, too.
Oh, okay.
So I'm looking forward to that. All right. Let's get going tonight for the chapter 5. And I have to say that all of the topics in tonight's class could easily be a semester-long course in engineering school. And what we have to do is just hit the highlights, the important points, the things that are important for the upcoming multiple choice tests. So there's a lot that's going to be left out, but there are URLs at the bottom of most of the slides where you can go and follow through and get more information if something really intrigues you. So let's get started on section 5.1, semiconductor devices. And we have to start with the atom. Got to get back into science class, remember? So we've got the nucleus with the protons and neutrons. And orbiting around the nucleus are electrons. They're opposite in charge. There's all sorts of gravitational and other influences and whatnot going on. But it's the atom that actually controls the properties of a material. And one of the most common atoms in the world is the carbon atom. It's considered to be a very stable atom. Notice it's got 4 electrons in the outer shell, and it's got an equal number of protons in the nucleus. And so this is our standard look at an atomic structure. Now the outer electrons, those 4 that I showed you there, they're known as the valence electrons. And you can follow the URL there to get more information about that. But valence electrons, they go along with something called the octet rule. And this says that when atoms are bonded together in certain materials, the electrons occur in pairs, and the pairs often leave bonded atoms with 8 electrons in the outermost shell. Huh? What are you talking about? It'll come clear here in a picture just a second. So in order to get 8 electrons in the outer shell, some atoms will share electrons with other nearby atoms. And when they do that, then you have a very rigid structure, very well supported crystalline structure. And you're going to see that here coming up. So hold that thought about the octet rule and the valence electrons in an atom. So this is one of my favorite quotes. You may have heard it already. The nice thing about standards is that there are so many of them to choose from. When I first got involved in electronics back in the 1970s, it was the time of vacuum tubes and dinosaurs. Well, vacuum tubes anyway. And so I was originally taught the electron theory of current flow. And the electron theory of current flow said that electrons move from the negative source, a battery or whatever, and electrons flow around a circuit and come back to the positive. This is the electron theory of current flow. Well, at about the same time, semiconductors were becoming very popular, and it's easier to explain solid-state devices using not the electron theory of current flow, but something known as the conventional theory of current, and that is that current, not electrons, current flows from positive through a load and back to the negative. So I point this out because depending on the text that you look at or what you're talking about, you may be talking apples and oranges. Somebody may be talking electron theory, somebody may be talking conventional theory. They are both true, which you will see here on this diagram. We're looking here as a battery with a positive side on the left and the negative side there on the right. And you can see the electrons moving from the left to the right. And you can see the red there, the current flow moving from the positive to the negative. Did I get that backwards? No, I think I'm right. And so both conditions are true. I point this out because it becomes interesting in semiconductors. And what are semiconductors? Well, conductors are copper, gold, silver, things that will conduct electricity very well. Insulators, glass, plastics, ceramics, are things that do not conduct electricity. And of course, then semiconductors are somewhere in between. And probably the most common and popular semiconductor material right now are silicon. Silicon atoms, notice the 4 electrons in the outer ring, the valence ring. And so here we have the model of a silicon atom. And when silicon atoms get together, they combine with those outer electrons and they make this matrix. They make this really strong bond across each other. It's a crystalline type material. In fact, if we look at the calculator cam just for a second, thanks to Vicki and Dave, Ivy, here is a chunk of silicon. Notice how shiny and solid it is. So this is because of all of those bonds between the various atoms in the silicon. This is what semiconductor material looks like, no matter what type it might be. And so if we look at, again, another view here of silicon atoms as electrons move through the silicon atoms from one side to another, it doesn't happen naturally with pure silicon. In fact, pure silicon is an insulator. What we have to do is we have to modify the silicon slightly. And how do we do that? We do something called doping. We contaminate the silicon with a special material. We'll talk more about that in a second. So semiconductor materials have been around for a really long time. In fact, the first radio maybe that you ever listened to might have been a crystal radio. And good to listen to high-powered AM stations in the area. You're not going to get your FM station on this one, but they used galena crystals, also known as lead sulfide or lead glance. And you see there on the right, in fact, let me turn on my laser pointer as soon as I get my cursor here. So note here, there's a wire. Yes?
When they take those big chunks like you just had
Yeah.
of the galena or whatever, sulfide, how do they get them into the little pieces of electronical?
We'll talk about it. We'll talk about it here in just a second. So what you saw there was raw polycrystalline silicon. That's what we were looking at, and this is polycrystalline galena. And what we have here is on this arm we have a wire that comes down and is touching the galena crystal at one point. And this is the trick. You had to find a good point on the lead glance, the galena, and then it would act as a diode. and it would be a nonlinear device, and it would be able to capture the modulation from an AM radio station and send that energy off to headphones. So this is the first use practically of semiconductor materials in radios, or one of the first anyway. Now the first transistors, remember back in the 1970s when I was learning, the first transistors were not silicon. The first transistors were germanium. And they're still used in some solar panels and other electronics. Take a look at it. Looks kind of similar, huh? All right, again, 4 electrons in the outer ring. And here again is an animation of the germanium atom. Germanium had some problems, though. It was electrically leaky, and the transistors did not last all that long. They were also susceptible to static charges, and so that's when they moved to silicon, which is more stable. Now, this is polycrystalline silicon. We'll look at another picture here in a second. Again, notice the electrons in the outer ring, 4 of them there. And we've already seen how they will come together. All right, so here's the answer to your question. And the reason I know that, come back to me just for a second. In my former life, I used to work for the Dow Corning Corporation, which was a joint venture between Dow Chemical Company and the Corning Glass Works. Now, Dow Chemical has been absorbed into or joined with DuPont. Now it's a whole different ballgame. But back then, Dow Corning, at their facility in Hemlock, Michigan, made, well, they made polycrystalline silicon from sand. That's how it's made. Then, well, let's take a look at the picture. Come back to the laptop for a second. So here's our polycrystalline silicon, which they would make out of sand. Then they would have a perfect crystal of silicon in size and shape, and they would be right at the tip here, and they would melt under high heat and stress the silicon, and it would reform and come out as a cone. And then here, this is single crystal silicon, and this is what you make integrated circuits and other large-scale devices out of, the single crystal silicon. And this tube of silicon, might be 4 feet long or something like that, is sliced into wafers, and then the electronic circuitry is through some sort of electronic lithographic technique. I don't even know. The circuits are imposed on the single crystalline silicon. So there's an answer to your question. I hope it's satisfactory. All right. Dope. Remember I said that semiconductors in their raw state are really pretty much insulators. But what we need to do is we need to add a dopant material, just a tiny bit, and then we can turn it into one or another type of semiconductor material, N-type or P-type. When silicon is doped with phosphorus, it's called an N-type crystal. And when silicon is doped with the element boron, it's called a P-type material. And the difference between the two is that in the N-type material, it has an additional number of electrons in there. So electrons move freely through that material. In P-type material, it has a number of absence of electrons, for want of another term, or holes. And so this also becomes a free carrier. And the trick is when you put N material next to P-type material, then you get your most basic semiconductor device, a diode, and we'll talk more about that. But so here we have silicon atoms with a little bit of phosphorus that is donated some additional electrons, and it allows then electron current flow in the material. P-type material with boron, it actually has an additional hole. So remember, P-type material has excess holes. N-type material has excess electrons. And in semiconductors, you can have something called an acceptor. An acceptor is a dopant atom that when added to a semiconductor forms the p-type region. So if you hear something acceptor, that means you're adding holes to the semiconductor. When you're hearing about a donor, you're adding additional electrons to the material, forming an n-type region. So here's an animation of some doping going on. They're using silicon and indium as the dopant here, and they're turning it into a p-type material with an absence of electrons or an addition of holes. And that's how an active semiconductor material is created. And as I mentioned, when you put p material next to n-type material, we end up with diodes. In the book, in this chapter, they talk about 8 different kinds of diodes. So we're going to go through all of them, make sure that we have an understanding of them. Again, this is, we could go on for hours and hours and hours about this. The most basic diode is a junction diode, when you have p-type material next to n-type material. And what it does is it allows current to flow in only one direction. If we have a positive voltage here, it will flow in this direction, but if we put the positive voltage on this side, it is blocked by the nature of the materials. And that corresponds to, this is the schematic symbol for a diode. See the arrow, positive will flow that way, but positive is blocked that way. And this is known as the cathode of the diode. This is known as the anode of the diode, and the cathode is always marked physically on a diode with the stripe. Diodes fail due to too high temperatures, and too high temperatures are a result of excess current flow. All right, I don't know how many of you are as old as I am. You remember disco? I want to introduce you to the Gap Band. The Gap Band? Remember the song? Baby, you dropped a bomb on me. No, I can't play it because we get a copyright strike. All right, that's the Gap Band. Well, for us, we're not going to talk about the Gap Band. We're going to talk about the band gap. This is my way for you to kind of remember it. And the band gap exists at an atomic level as the energy required for electrons and holes to transition from one material to another. It has a lot to do with the electrical conductivity, and here are all the definitions. What we as technicians, and I don't consider myself an engineer, I consider myself a technician, what we deal with because of the band gap is something that we call the depletion region of a diode. And that's this area here. If you put P material right next to N material, there's a repellent phenomenon going on, and there's no current flowing whatsoever. And if you put 1/10 of a volt going to this material, it still won't go. 4/10 of a volt, no, still won't go. But for silicon, 0.7 volts is, this is electron flow here, then you'll get current flowing. So this is known as the diode's voltage to overcome the depletion region, the self-bias voltage. And if you reverse bias a diode, there's no conduction whatsoever. Here's an animation that maybe makes it a little simpler. As we apply voltage to the diode, the depletion region gets smaller and smaller until finally you get full current flow. And this depletion region is interesting. For germanium, it's 0.2 volts. For silicon, it's 0.7 volts. And for another type, gallium arsenide, it's 1.2 volts because of this band gap at the atomic level. So just be aware of that. Diodes come with different ratings, the amount of current that they can handle, and also the peak inverse voltage. How much reverse voltage can you put on that diode before it's going to break down? But remember, diodes tend to fail because of high temperatures. They tend to fail because too much current overheating the diode and causing it to catastrophically fail. So that is our first diode type. The second diode type is the Schottky diode. In this case, you don't have p-type material. All you do is have n-type material, and the p material is replaced by a metal connection. It's used in power circuits primarily, and it has a lower voltage drop. Even though it's silicon, its voltage drop is 0.2 volts. And you can tell in the schematic the Schottky diode because this kind of looks like an S. And don't be fooled if they put it in the schematic backwards. It still looks like an S if you looked at it in a mirror. So this is a Schottky diode. If you have in your ham shack battery backup, for example, and you have a power supply, you can buy a device that goes in between, and if the power supply fails, the battery immediately comes online. That's using Schottky diodes for power handling. Point contact diodes are very much like that crystal radio that we looked at. In fact, if you look at the pictorial here, we have our wire lead, and we have a little pellet of germanium for the 1N34 diode, for example. This is a detector diode. It's used for detecting AM signals or useful in metering and other things. It's a low capacitance RF applications. This is a point contact diode. Hot carrier diodes are a kind of a Schottky diode in that there's no p-type material, but it adds a metal dot to the metal that is going to the end material. And what it does is it makes it very fast, a nice high-speed diode, good for UHF and VHF mixing or detecting. So this is a hot carrier diode. See, it is a kind of a Schottky diode because it still has that S symbol there. But hot carrier diodes are good for UHF and VHF mixers. Number 5 of 8 is the Zener, or I've heard Zener diode. Normally these are put into a circuit in a reversed biased state, and in that case it's got a region here, this long region, where it will hold a voltage pretty much constant. And it's this property that makes it an excellent voltage reference. So in regulated power supplies, most all of the time you'll see them use Zener diodes as the reference for the rest of the regulator stage. And it's because of the voltage being held constant in this reverse bias condition. You can have a tuned circuit with an inductor and a capacitor. And the capacitor could be two metal plates separated by an insulator, but the capacitance could also be that of the depletion region. And if you make a diode specifically for this case, you can use the depletion region as a tuning element in a circuit. And so this is what we call a varactor. And it used to be a big deal back in the day of analog television that the Zenith TV has varactor tuning. That meant it didn't have any physical plates or whatnot moving around. Rather, it used diodes, the capacitance of the diodes, to change with the varying voltage and to change the tuning of a resonant circuit. You may have a linear amplifier in mind, for a Christmas purchase this year. And if you're going to look for one and you do Morse code, you probably want to do full break-in. You want to be able to hear between the time when you're transmitting. And pin diodes are what makes this possible. It's a diode with p-type material, undoped material known as intrinsic, and n-type material. And pin diodes have a special case where the amount of forward bias through the diode controls the level of RF conduction. So you can actually vary the amount of RF current through the diode by the DC that flows through it, or you can actually block it so there's no RF coming through. And so the transmit-receive switches and high-powered amplifiers, for example, that are full break-in, they're using PIN diodes. P material, intrinsic material, and N-type material. Now, one thing about these is you got to make sure that you don't have a diode that has a lot of inter-element capacitance between the P and N, because that kind of bypasses what you're trying to do. I mean, literally, you can bypass RF around the diode. So PIN diodes are always designed to have a very low junction capacitance. And when they're put into an RF switching or an RF level control circuit, again, it is the amount of forward bias that determines the amount of RF conduction. And last but not least, light-emitting diodes. LEDs are diodes that emit light when forward biased, and always they're going to have something here called the current limiting resistor, because if you directly connect an LED up across a power source, the unlimited current will burn it out almost immediately. But LEDs have replaced lamps for indicators and pretty much anything. And even LED light bulbs now are designed such that you can get very high illumination out of LEDs. So what's ahead in semiconductor technology? So this is actually an older discussion, but it's still true. And these devices are coming online now. We mentioned gallium arsenide. There's another version of this. Gallium arsenide is a semiconductor material that's being used in military applications for ultra-high radio frequencies and very fast electronic switching. They also have a very low noise as compared to silicon. Notice what it looks like. Yeah, we've seen that before. So that's gallium arsenide. It's 6 times faster than silicon. So I've actually seen some solar panels now that have gallium arsenide in them, and some high output panels. The problem has always been that a single wafer of silicon, remember I told you the slices out of that tube, costs about $5. A single wafer of gallium arsenide is about $5,000, at least at the time of this article. But its output power is much, much higher due to its higher electron mobility. If you look here, it's way up here on the chart. It's the speed with which electrons move through semiconductors in the presence of an electric field. So that's gallium arsenide. Another gallium compound is gallium nitride. Also very good. It has 1/10 the resistance of silicon, so that gives you higher energy efficiency, faster switching, and it's primarily used in MMICs. We talked about this in the general class. These are the monolithic microwave integrated circuits, devices that look like this. Well, Gary, I don't have any of those. Oh, yes, you do. Your cell phone is chock full of these. MMICs are RF amplifiers on a chip or a block, and their characteristics are that they have standard input and output impedances, usually 50 ohms. They have very controlled gain and low noise, and the output of the device, wherever that is usually where you put the DC power into that device through a choke or a resistor or something like that. So notice 3 answers here. Okay, that's a clue. And with MMICs, they go along with monostrip construction or microstrip construction. It's a precision printed circuit board with a conductor on one layer and the ground plane on another layer. And these are the devices that bring connections to the MMIC and take them away from the MMIC, microstrip construction. All right, back in the 1970s, we were transitioning from vacuum tubes to transistors, and the first transistors that we had the opportunity to deal with were bipolar transistors, using silicon or germanium, P and N type material. But unlike the diode where you have P and N, in a transistor you have 3 layers, PNP, or NPN. Those are the two types of bipolar transistors. And here's the schematic symbol for a bipolar transistor. It is what we would say a low impedance device, and it's driven by current. Current has the major influence on it. And it has three legs: the emitter here, E, the base, and the collector. And you can put the transistor in different configurations. This is known as the common emitter configuration, because you see emitter is taken to ground here. And you have the input coming in on the base, and the output is taken from the collector. So this is a common base bipolar transistor. The arrow points toward the N-type material. So this is an NPN transistor. And with a silicon transistor, the voltage between the base and the emitter is going to be around 0.6 volts. And that's actually a good troubleshooting tip. If you want to know if a transistor might be dead, just measure the base emitter voltage. And if you don't have 0.6 volts there, I'd continue to look, because there's an issue there. Maybe the transistor is opened up or shorted out. Transistors have measurements for gain and other things. They're called hybrid parameters, or H parameters. And the transistor's gain in the common emitter configuration is known as its beta. It's the ratio of collector current to base current. And this could be DC current, or it could be AC current. You can have the DC beta and AC beta. Normally they're just about the same. And so here we have a pictorial of a common emitter circuit with the base as the input and the collector as the output. So the HFE, also known as beta, this hybrid parameter, is an indication of gain of the transistor. Now, another configuration that you can put a bipolar transistor in is the common base configuration. And in this case, the gain is measured as the alpha, or the collector current divided by the emitter current. And the value is usually less than 1 because of the way a transistor divides current up. But just know that the common base current gain in a common base circuit is known as the alpha. And the alpha and the beta cutoff frequencies are that at which 1 kilohertz signal is used as a reference, and then the frequency at which the gain falls off to half power, that's known as the beta cutoff frequency. That's in a common emitter configuration. In a common base configuration, it's the alpha cutoff frequency, and those are about the same as well. Those frequencies will be about the same. But the alpha cutoff frequency, they're talking about a common base configuration. We're moving right along. I know this is a lot to absorb, but just hang in there. And there's a lot more detail that you can look into to find out more about these things. So those are bipolar transistors, just a brief look at them. The next type that came along were field effect transistors. And unlike the bipolar transistors, which were low impedance devices and current driven, field effect transistors are likened to high impedance devices, voltage driven. And field effect transistors are much more like vacuum tubes than are the bipolar transistors. But if you don't have to deal with vacuum tubes, don't worry about it. And here we have a field effect transistor. Remember, the arrow is pointing toward the N-type material, so this is an N-channel field effect transistor. And it has, instead of base, collector, and emitter, it has source, gate, and drain. So this is the gate, this is the source, and this is the drain. Or did I get backwards? Maybe this is the source, and this is the source. That's RS. Source, and this is the drain up here. All right. See, I don't do this very often. And you can use surface mount device field effect transistors in such things as low noise UHF preamplifiers. So those are the little devices here on the printed circuit board, probably using microstrip construction here. And these typically have a 0.5 dB noise figure. They're not adding a lot of noise to the signal that they're trying to preamplify. That's a pretty good thing. So junction FETs, we mentioned, are voltage controlled, and they're the simplest kind of field effect transistor. Now we went beyond this though to MOSFETs, metal oxide silicon, and these FETs have two different types. Enhancement mode, where the device is normally off unless the gate is biased toward the drain voltage. That's the enhancement mode. Or depletion mode MOSFETs are those where the device is normally on. Current normally flows through it unless the gate is biased below a threshold voltage, and that turns the device off. So enhancement is off until you turn it on. Depletion mode is on until it's biased off. And here are the schematic symbols for that. Here is a depletion mode. Here is an enhancement mode. Note the separation here in the channel. And the arrow always in bipolars and FETs point to the N-type material. So both of these are what we would call N-channel field effect transistors. And in metal oxide silicon FETs, you generally have Zener diodes that are placed back to back here for static protection, because FETs can be very, very sensitive to static. The front end of your radio, if it's a super heterodyne radio or a modern radio design, likely has an FET front end, and they've got this circuit in there. All right, let's see. Let's answer some questions. So go ahead and unmute, and remember, please, our 3-second rule. So in what application is gallium arsenide used as a semiconductor material?
Charlie?
Charlie, it's a very fast, so very high frequency circuits, so microwave. It wouldn't be used in high current or high power, no, and very not low frequency, so it's high frequency. So which of the following semiconductor materials contains excess free electrons?
Alpha.
Alpha?
Yes, alpha. N-type material has free excess electrons. And why does a PN junction diode not conduct current when reverse biased?
Alpha?
Not alpha. If a diode is reversed biased, that depletion region in the middle is not going to get smaller, it's going to get wider. So here's the answer. Holes in the P-type material and electrons in the N-type material are separated by the applied reverse voltage and widen the depletion region. So what is the name given to an impurity atom that adds holes?
Charlie?
Charlie, that's an acceptor, yeah. And how does DC input impedance at the gate of a field effect transistor compare with that of a bipolar transistor?
17. And they're all voting no this November.
Charlie?
Charlie, yes, an FET has a higher input impedance. FETs are high impedance devices. And what is the beta of a bipolar junction transistor? We covered this awfully fast, I recognize.
Bravo.
Yeah, beta is another way to talk about gain of the transistor in a common emitter configuration. So that means the output is the collector, and so it's the change in collector current with respect to the change in base current. So a little bit of change on the base is going to give you a big change on the collector. That's going to give you gain. So which of the following indicates that a silicon NPN junction transistor is biased on? What's a good troubleshooting tip? Delta, yeah, the base and emitter voltage for a silicon transistor should be about 0.6 to 0.7 volts. And what is the term for the frequency at which the grounded base current gain of a bipolar junction transistor has decreased to 0.7 of the gain obtainable at 1 kilohertz?
Delta.
So it's common base, so it's just going to be the alpha cutoff frequency. Common emitter would be the beta cutoff frequency, but common base is alpha. Yeah. So what is a depletion mode field effect transistor? By adding bias, you deplete current flow.
Alpha.
Alpha, yes, an ET that exhibits a current flow normally between the source and drain when no gate voltage is applied. Yeah, yeah. You could spend hours and hours on these. All right, so here in these schematic diagram symbols, which is the schematic symbol for an N-channel dual gate MOSFET? Remember, the arrow always points to N-type material. So it's dual gate.
Bravo.
So bravo,
Yeah.
did everybody see that?
Yeah.
Gate 1, gate 2, pointing toward it, so that's an N channel. Indeed, bravo, number 4. All right, which is the schematic for a P channel junction FET? Junction is the most basic kind of FET, yeah, alpha. Arrows pointing away from the channel, so it's a P channel. Yeah, good. So what is the purpose of connecting Zener diodes or Zener diodes between a MOSFET gate and its source or drain?
Delta.
Yeah, protect the gate from static. And what is the most useful characteristic of a Zener diode? You hear it pronounced both ways, Zener or Zener.
Bravo. Bravo.
Yeah, constant voltage. Zeners are constant voltage. And which characteristic of a Schottky diode makes it a better choice than a silicon junction diode for use as a power supply rectifier?
Delta.
Yeah, it has a lower forward voltage drop, 0.2 as opposed to 0.7. And what property of an LED's semiconductor material determines its forward voltage drop?
Alpha.
No.
No.
This has to do with this depletion
Bravo.
region. Bravo, the band gap.
Oh, bad gap.
I didn't bring in the LEDs, but yeah, so yeah, that's it. So what type of semiconductor device is designed for use as a voltage-controlled capacitor?
A.
Yep,
A.
that's the Varactor.
Velociraptor.
Velociraptor diode, that's what we want. So what characteristic of a pin diode makes it useful as an RF switch? Or what does it have to have?
D.
D, it has to have low junction capacitance. They designed them that way. So you can't leak RF around it. So which of the following is a common use of a Schottky diode?
U. Delta?
E.
Yeah, so certain kind of Schottky diodes can be used as a UHF, VHF mixer or detector. And what causes a junction diode to fail from excessive current?
Bravo.
You
Bravo.
let the smoke out. Yeah, excessive junction temperature. So which of the following is a Schottky barrier diode?
A.
Yeah, you've got N-type material and no P-type material, just a metal. Yep. So what is a common use for point contact diodes?
E.
Think 1N34, the little guys. Yeah, that's an RF detector. It kind of looks like a little crystal radio in a little device. All right. So in this figure, which is the schematic symbol for a Schottky diode?
B.
Beta. Bravo.
Bravo.
Number six, yeah, B. And what is used to control the attenuation of RF signals by a pin diode?
Alpha.
Alpha.
Yep, the forward DC bias current will determine whether it's going to conduct RF. And why is gallium arsenide useful for semiconductor devices operating at UHF and higher frequencies?
B. B.
Yeah, that's that chart I showed you there. It has higher electron mobility. And which of the following materials supports the highest frequency of operation when used in mimics?
Delta.
Yeah, it's also going to be the most expensive. Yeah, the gallium nitride. And which is the most common input and output impedance of mimics?
Alpha.
Alpha.
Yeah, our standard input and output 50 ohms. Yeah. And which of the following noise figure values is typical of a low noise UHF preamplifier?
Alpha.
Yep,
Alpha.
0.5 dB. And what characteristics of mimics make them a popular choice for VHF through microwave?
Delta.
See that? It is delta. Controlled gain, low noise figure, constant input and output impedance over the specified frequency range. And what type of transmission line is often used for connections to mimics?
Delta.
Microstrip. And how is power supplied to the most common type of mimic?
Charlie.
Yep, through a resistor or an RF choke connected to the output lead. They don't have a separate DC power connection. So what is microstrip?
Delta.
Delta.
Yep, you got it. Precision printed circuit conductors above a ground plane that provide constant impedance interconnects at microwave frequencies. Great. All right, let's do to section 5.2 and then we can take a break. We mentioned light emitting diodes earlier. Did you know they were invented in 1927 by a Russian? You can follow the URL and get more information. And did you know that all diodes emit light? I didn't know this either, but they're put in a case so you can't see it. Who knew? All right, so light emitting diodes, first practically used in 1962 when you have forward bias of the diode, it emits light. And the diodes have anodes and cathodes, and they give off the light in various color ranges when they're forward biased. You always have to have the current limiting resistor, usually about 100 ohms or something like that, just to keep the brightness under control. You can adjust that to get brighter or dimmer, but you can't hook it up directly to a power source. All right, another kind of semiconductor device is a charge-coupled device, not so much used anymore, but it has a history that you sample an analog signal, in this case light, and pass it in stages from an input to an output through circuits, and that then reconstructs the image that comes in from a lens to the CCD. Liquid crystal displays are popular. It turns opaque, the liquid crystal does, when voltage is applied. It is somewhat hard to see, though, when you're using polarized filters. I have a Chevy Avalanche from 2009, and if I put my sunglasses on, I can't see some of the things on the panel because they're using liquid crystal displays. This was my first impact with semiconductor devices, the electric eye. The first thing that registered with me anyway. It's a photoresistor, also known as a photocell, whose resistance changes with the illumination level. And it uses the property of photoconductivity. So with a photocell, more light equals more conductive. And you have to think about conductivity versus resistance. The more conductive it is, the lower the resistance. The less conductive something is, the higher the resistance. And it first impacted me back in Saginaw, Michigan, going to downtown Saginaw to, of all places, the Montgomery Ward store. It looked kind of like this. And I walked up to the door of the store, and they opened automagically. How did that happen? Well, because they had a visible light source at one side and a photocell at the other. And when I walked in and interrupted the beam, the doors opened. The conductivity of the photocell went up. The resistance of the photocell went down when the light was shining on it. But when I blocked it, then the reverse took true. And the photocell was probably constructed of a material like selenium. Selenium was an early semiconductor used in photo light meters, for example. Notice what it looks like there? Hey, there's our crystal material. Same kind of thing goes on in modern circuits now, in certain integrated circuits, and they're known as optocouplers or optoisolators. And they can be just a little 4-leg dip package here, where you have a light-emitting diode on 2 of the pins and a phototransistor on the other 2 pins. And when the current flows through here, it lights up the transistor, and then current can flow through here. Well, why is that important? Why would you want to do that? Well, with switching power supplies nowadays, they don't have transformers like they used to isolate you from the 120 or 220 volt input power. And so this is a schematic I think I got from Poland. But here is an opto isolator or optocoupler that is monitoring the output voltage, and this provides feedback to the switching circuit back here so that the output voltage is regulated, but at the same time it keeps the output side isolated from the mains voltage. There's no transformer here, so this is all potentially lethal if you were to touch it. So that's where the optocoupler, optoisolator, that's the isolator part where it keeps things safe. Solar panels are another way that we use the photovoltaic effect, converting light into electrical energy. Each panel consists of multiple silicon solar cells. And here's a definition. The relative fraction of light that is converted to current is known as the solar cell efficiency. So dirt can actually impact a solar cell's efficiency if you block the amount of light you can't get through. Each solar cell in a panel outputs roughly a half a volt, and the panel is made up of a number of solar cells in series. And the photovoltaic effect are where electrons are shifted into a higher orbital state by the photons from the sun. And I'm blessed that I've been able to install a very large array of solar panels, 13 kilowatts worth, and they come into my garage. And inside my garage, I have one of these, a Solarc 15K inverter. And what the inverter is able to do is to take the DC energy from the solar cells and convert it into energy for my house, AC, 120 and 240 volts for use in the house. It also has interconnectivity to batteries as well. So that's what an inverter like my Solarc does, is it converts DC from solar cells or from batteries to AC for use in your house. That's an inverter. All right, moving on to a new topic. Remember in the day when you had to restring a dial cord? Did anybody ever have to do this? That's how we used to tune radios, is that you'd have a variable capacitor here, and you'd have a tuning knob someplace over here, and you would turn it, and it would actually turn the physical capacitor. But the dial cord would always break, and they all had different patterns of how to string the dial cord. It was a nightmare. Nowadays, we use optical shaft encoders, also known as rotary encoders. It's a knob or a shaft with an encoded pattern like you see here, and the pattern is read by optical sensors, and the sensors can determine whether you're going clockwise or going counterclockwise, and tuning up or tuning down. So these are optical shaft encoders. Another modern replacement, the old mechanical or electromechanical relay. Solid state relays are available as well, where you can have an input circuit and that control a contact on the output side. And this might be something that you would need to interface an old linear amplifier that might have a 100-volt switching circuit for push to talk. Well, your modern radio won't maybe be able to handle 100 volts at the current, so you can put this in between to protect your modern radio, and at the same time still switch the push to talk circuit in your older linear amplifier. All right, let's answer some questions and then we can take a break. What absorbs energy from light falling on a photovoltaic panel?
Charlie.
It's the electrons. You're moving them into a higher orbit. And what happens to photoconductive material when light shines on it?
Bravo.
Alpha.
No, not Bravo.
Alpha.
Alpha.
Yeah, when light shines on it, it becomes more conductive, so the resistance decreases. So what is the most common configuration of an optoisolator or optocoupler?
Delta.
Delta.
Yep, an LED and a phototransistor. And what is the photovoltaic effect?
Baker.
Yep, it's the conversion of light
Bravo.
to electrical energy. Yep. And which of the following describes an optical shaft encoder?
Alpha.
Did I hear alpha?
Yes, alpha.
I hope I heard alpha. Yeah, it's a device that detects rotation by interrupting a light source with a patterned wheel. And which of these materials is most commonly used to create photoconductive devices?
Charlie.
Some sort of crystalline semiconductor. Silicon, selenium. So what is a solid-state relay?
Bravo.
Bravo.
Yeah, Bravo is correct. A device that uses semiconductors to implement the functions of an electromechanical relay. So why are optoisolators often used in conjunction with solid-state circuits that control 120 volts AC?
Charlie.
Charlie.
Yeah, optoisolators provide electrical isolation between a control circuit and the circuit being switched. And what is the efficiency of a photovoltaic cell?
E.
Delta.
Yeah, it's the relative fraction of light that is converted to current. So what is the most common material used in power generating photovoltaic cells?
Charlie.
Baker.
Baker, silicon. Silicon solar cells. And what is the approximate open circuit voltage produced by a fully illuminated silicon photovoltaic cell?
Bravo.
Alpha.
Alpha, 0.5 volts. And what is the purpose of an inverter connected to a solar panel output?
Delta.
Yep, it converts the panel's output from DC to AC. And ladies and gentlemen, you have done yeoman service. It's 35 minutes after the hour. Let's go ahead and take a 5-minute break, and then we'll tackle digital logic in less than an hour. Oh my God. We'll be back. Thanks.
Well, I guess I have to rewatch that chapter.
Like 6 times.
I have to do apologize. I sneaked the burrito in there. That's why I went dark. How many in the classroom now?
you may not feel like it, but really you're doing great. There is just so much information that we covered in just a very short period of time there. And we're planting seeds. So we want you to go back and review the videos, reread the chapter in the book. And the more you do that, the more aha moments you will have. You'll go, ah, that's what he was talking about. So there is method to our madness. You can do it. Keep going. All right. This is the last section, I believe, section 5.3, digital logic. In less than an hour. Oh my gosh. So we have analog signals. We're looking here at signals in the time domain. So we have amplitude on the vertical scale and time over here. And analog signals could be positive, they could be negative, they could be someplace in between. Digital signals, on the other hand, in the time domain are either on or off. Or they're either one voltage or another voltage. And we don't know necessarily what those voltages are, but that's ones and zeros is another way to look at it. And when we do that, we're actually talking about something called Boolean algebra, named after George Boole. I believe he was British. And back in the 1800s, he came up with the idea of an algebra just based on true or false, 1 or 0. And his work is actually fundamental to digital electronics. And like any mathematical system, he had various axioms in there. And if you're a math major, you'll know what all of these are and how they can all be used. So that's great. But this is back in the 1800s. Electronics weren't even out there. But they did have a concept even back then, positive or negative. Positive logic is defined as when a higher voltage represents a 1. High is a 1, low is a 0. That's positive logic. Positive is 1, 0 is a 0. Negative logic defines a low voltage as being 1. And the trick is that an OR gate in positive logic is the same as an AND gate in negative logic. What? And an AND gate in positive logic is the same as an OR gate in negative. It used to be back in the day that chips were really expensive, and digital designers could, in one circuit board, switch from positive logic to negative logic and then back again. Not done so much anymore, but I want you to know about it and know the positive logic. It's in blue up there. That's a test question. So here's some logic gate analogies here using switches. This is an OR gate, and you can see that the lamp lights up if A is closed or B is closed. Or you could say if A is true or if B is true. Or you could say if A is 1 or B is 1, you'll get an output. They've indicated there is Q on the lamp. So this is an OR gate. Either or both would cause the light to illuminate. That's an OR gate. An AND gate requires that both A and B be true. If A and B are true, then you get an output. Or if A is 1 and B is 1, then the output will be 1. This is an AND gate. And in the real world, the first diode gates, or the first gates that came out, were based on diode logic. It's the most simple kind of thing, and I've actually used this sometimes in circuits when I've had to quickly rig up something to work. But it doesn't matter what devices you're using for logic, the logic truth tables are the same. And so you can look at these closer when you get the handout here, but we have AND gates, NAND gates, OR gates, NOR gates, and a NOT gate. Well, the NOT gate is just a simple inverter. If A is 1, then the output will be 0. If A is 0, then the output will be 1. That's called a NOT gate. also known as an inverter, and that's what this circle on the output indicates. This is an amplifier with this circle. That means it's inverting. An OR gate, yeah?
Is that final under a binary code?
Yes, it's binary math, yes indeed.
Thank you.
An OR gate, and we're dealing now with digital logic, but it's based on these mathematical symbols. An OR gate is where one or the other, if they're true, then the output will be true. So you can see the numbers here rolling through, and you can see the output Q there is changing. And here's the truth table for an OR gate. With the conditions of the A input or the B input, here's what the output is going to be. This is an OR gate. Here's an AND gate. Oh, by the way, OR gate, notice the letter O is rounded. Notice this curve. I always think of this curve as part of that letter O. So that's OR gate. Whereas the letter A for AND gate is straight. It's straight on the sides. So straight line means AND gate. And with an AND gate, you have to have both A and B be true, or ones, in order to get a 1 on the output. All right, we're going to throw one at you. Here's an exclusive OR gate, which is where one or the other is true, then you'll get a true on the output. But if they're both true, it goes to 0. So just know about these. There's not so much digital chip design going on anymore because it's all being done in a different way. But here are the logic gates, and the AND gate, OR gate, a buffer amplifier, the exclusive OR, a NAND gate, which is an AND gate with an inverter, the dot, a NOR gate, which is an OR gate with an inverter, the inverter itself, and an exclusive NOR. Oh my gosh, all right. So as I mentioned, diodes are the easiest kind of logic, and the first chips came out with diode transistor logic, DTL. You can't find these anymore. These are completely obsolete. But beyond DTL, we came to TTL, transistor logic, and had transistors on the input and the output. But the problem was that this is the output line, and it only had a single transistor here that would pull this line down to ground or up. And this could not be connected to a lot of other diodes. It had what we call limited fan out. We'll talk more about fan out here in a second. TTL, well, okay, between 0 and 0.8 volts DC was a low state. Between 2 and 5 volts DC was considered a high state. This in-between area here, though, was the uncertain zone. We don't know whether it's a 1 or a 0. And this is something that designers had to pay particular attention to when they're interconnecting gates one to another, and if they interconnected too many, you'd have problems getting into this uncertain region. And you never knew what the chip decisions were going to be at those levels. Here's another look at that indeterminate zone there in the middle that you always needed to avoid with TTL. And one thing that they could do is actively add resistors to certain circuits, inputs or outputs. They had both pull-up resistors and pull-down resistors. And so when there was no signal coming into the input, for example, the pull-up resistor would tend to pull the input of the gate high. So just be aware of something called a pull-up resistor. You could also have pull-down resistors as well. They re-engineered the TTL chips, and they came up with something called totem pole output, or 2 transistors, one to pull the output line high and the other to pull the output line low. That helped. That increased the fan out. And the fan out, again, is the number of additional circuits that you can put after the output. Gates with a larger fan out, could do this, but they tend to be slower in speed. Okay. We went from TTL, transistor logic, to CMOS. TTL chips were fine, except they used a lot of power. You had to build big power supplies to power TTL circuits, and they got really hot. So you had to cool them. Well, then along came CMOS, complementary metal oxide semiconductor, and MOSFETs in this case are used to implement logic gates. CMOS uses much less power than TTL, and it has greater noise margins because its switching threshold was at half of whatever the voltage supplied to the chip was. So if it was 5 volts, it would be half of that. So CMOS was an improvement. Didn't have to build the big power supplies, didn't have to do all the cooling. And then they came up with something called BiCMOS, which used bipolar and CMOS together. And in doing so, you got a high impedance input and a low impedance output. It was kind of the best of both worlds. And that had a kind of a limited lifespan. But CMOS and TTL you probably still can come up with. So gates, as we've talked about them, can be connected into circuits. And one of the more basic circuits is something called a flip-flop. Here is a set, reset, or an SR or RS flip-flop. It's a bistable circuit. It has 2 stable states, and it latches. We're not going into the design of why you would do all of this, but you can make lots of logic solutions using these gates. Later on at Texas Instruments, Jack Kilby, an engineer there, added a clock input, the C input, to a set reset gate, and he called it a JK flip-flop after himself, Jack Kilby, sorry. And but this was a real breakthrough because this clock input would cause the set reset flip-flop, or the JK flip-flop, to change states. And then when it would change states, it would actually divide the frequency. And it would divide the frequency on the input side of the clock, it would divide it by 2. So one JK flip-flop with pulses coming in on the clock, you could divide by 2. If you had 2 JK flip-flops, you took the output of one and put it to the clock input of the other, then you'd be dividing by 4. Then another, it would divide by 8, and then another you'd be dividing by 16. And this was a very important improvement. Again, remember, we're just hitting the highlights here. This is not trying to be detailed in any way. So these are flip-flops. Now, they had 2 stable states, remember? You can actually design a circuit so that it doesn't have a stable state, but actually it is a digital oscillator, or it's a clock oscillator, if you want to call it that, or a signal generator. Those are astable multivibrators, and they can be built with just transistors. And so you can see that the circuit is oscillating at a particular frequency, and the output pulses could be taken from either of the 2 transistors here. This might be used for clocking to control certain circuits. And that's an astable multivibrator. Monostable multivibrators are things that have only one stable state, and it produces a single output pulse when triggered externally. So here's our circuit here, and we've got a switch, and it goes over here. Okay, well, why don't we just put the switch on the output? The problem was switches get dirty. Switches have bad contacts over time, and so if you had a mechanical switch and you pushed it, it might actually open and close a couple of times because of the dirt. And in a digital circuit, that's no good. And when you're pushing a button, you want one pulse and one pulse only. So they would do these monostable multivibrators. Here's another version of it. They're also known as switch debouncing circuit. That noise that was called a bouncing switch. So this is a debouncing circuit that you would have a trigger that would be a very short duration coming in, and you'd get a certain constant output on the output. And a lot of circuits were used like this to help electronics. You know, when you commanded it to do one thing, it wouldn't do three things. That's a monostable multivibrator. Bistable multivibrators are ones which have two stable states. In this case, they can be direct coupled. It's a flip-flop. It's a flip-flop using transistors. And a decade counter. It's an integrated circuit that has one output for every 10 inputs. So if you just take one of these LEDs and look at it, for every pulse that is coming into it, it will illuminate only once every 10 times. There. And then you have to wait. So that's a decade counter. It's counting tens. It has one output for every 10 inputs. And the integrated circuit was like a 4017B with dual inline packaging, one clock input, and reset and enable lines to control it. Another logic family that became popular for a while was the tri-state. No, not those tri-states, these tri-states, where a chip would have an output that could be high impedance, low impedance, that's the signal, 1 or 0, or it could be disconnected, high, low, or open logic states. And it used a chip select line or an output enable line, that's this right here, that would determine what state it was going to be in. It was called a tri-state logic, and this improved the ability to fan out, which we talked about earlier. Here's a tri-state buffer with the enable line here, and it enabled various bus lines for signaling, that you could have this drive the bus for a while, and then you could have this data circuit drive the bus for a while, and these are receiving the data signals and sending them out. So that's tri-state logic. Custom integrated circuits back in the day were pretty primitive. You actually could program your own logic device by blowing fuses. True. They had all these gates, and they had these fuses in here, and you would specify how the gate was to perform by specifically blowing little fuses inside the device, testing it. Okay, yeah, okay, got that. And it would do the thing you wanted to do. Now, the programming could happen only once. And if you wanted to reprogram it, you had to pull the device out and put something in. That's very primitive. Nowadays, we've come a long way, baby. We're using something called field programmable gate arrays, or FPGAs. It's a programmable logic device that can be reconfigured by software. And you can put just super complex logic on a single integrated circuit, and SDRs use these for a lot of their functions. And the FPGAs are very, very fast devices. Things are happening at hardware speed, and you program them using something called hardware description language. And the most common types are something called VHDL and Verilog. They're hardware description languages, much like software languages. You actually can program the chip to do certain functions, but these are gates and adders and registers and multiplexers, not what you would do with software. All right. Digital logic questions, here we go. So what is tri-state logic?
A.
It is A. It's devices that have a 0, 1, or a high impedance output state. And which of the following is an advantage of BiCMOS?
C.
Yeah, it has the best of both worlds. It has the high input impedance of CMOS and the low output impedance of bipolar. And which of the following digital logic families has the lowest power consumption?
Delta?
It is delta, CMOS, it is. And why do CMOS digital integrated circuits have high immunity to noise on the input signal or power supply?
Charlie?
Yep, the input switching threshold is about half of the power supply voltage. And what best describes a pull up or pull down resistor?
Bravo.
It is Bravo. It's a resistor connected either to the positive or negative supply used to establish a voltage when an input or output is an open circuit. You don't want an indeterminate voltage there. All right, in this figure, which is the schematic symbol for a NAND gate?
Bravo.
So it's going to be an AND gate with an inverter. Remember, AND is straight.
Oh.
So here's an AND gate, but a NAND gate is going to have a NOT or an inverter on the output. So it is in fact number 2, a NAND gate. And what is used to design the configuration of a field programmable gate array?
Bravo.
Bravo.
Yeah, hardware description language. All right, in this figure, what is the schematic symbol for a NOR gate?
Delta.
Delta.
Yeah, it's got the curvy for the O is an OR, and then here's the NOT, so it's a NOR gate. Great. And what is the schematic symbol for the NOT operation? Also inversion.
C.
Charlie.
Charlie.
Charlie is correct. It's a buffer amplifier. It's not changing this, but it's going to invert it right here. So, yep, number 5. So, which circuit is bistable?
Charlie.
It either
Charlie.
flips or it flops. A flip-flop. And what is the function of a decade counter? Decade is how many years?
Alpha.
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 It produces 1 output pulse for every 10 input pulses. And which of the following can divide the frequency of a pulse train by 2?
Bravo.
A flip-flop, or specifically the JK flip-flop with the clock input. So how many flip-flops are required to divide a signal frequency by 16?
A.
Alpha.
Yep, 4 of them. And which of the following circuits continuously alternates between 2 states without an external clock signal? It's generating its own.
Alpha. Delta.
Delta. It's astable. It's not stable at all. It's an astable multivibrator. So what is a characteristic of a monostable multivibrator?
Alpha.
Yeah, alpha is correct. It's a debounce, the switch debouncing. It switches temporarily to an alternate state for a set period of time. And what logical operation does a NAND gate perform? You might have to go back and review this because we didn't have much time to go through it tonight.
Delta.
It is delta. A NAND gate will produce a 0 at its output only if all inputs are 1. And what logical operation does an OR gate perform?
Alpha.
A.
Yep, alpha is correct. It produces a 1 at its output if any input is a 1. And what logical operation is performed by a 2-input exclusive NOR gate?
Charlie?
Charlie is correct. Great. It produces a 0 at its output if one and only one of its inputs is 1. That's the exclusive part. So what is a truth table?
Baker.
Yeah, it's a list of inputs and corresponding outputs for a digital device. And what does positive logic mean in reference to logic devices?
Rob?
Baker.
Yep. High voltage represents a 1 and a low voltage is a 0. And ladies and gentlemen, you made it through a very difficult chapter with some time to spare tonight. So let me unspotlight myself here in the Zoom classroom. Where to go? Oh, remove spotlights over there. And did we have any chats, any class chat activity tonight? Any questions, comments? The brains are fried, Dave. I've ruined them. Keep going. You can do it. Dave, what are we going to talk about next week?
Well, next week will be Chapter 6, and with all of our difficulties, I've had a few extra weeks to go through it all. So Chapter 6 will be divided into 2 halves. We'll be doing 6.1 and 6.2 for next week. I'll send out an email, but that'll let you get started on the reading. And it's another chapter that's jam-packed with information, technical data, and not a lot of calculations, which I think will be music to some people's ears, and we'll continue on.
All right. And with that, I'm going to release you early tonight. Thank you for your attention, and we will see you all next week. 73, y'all.
73.
Thanks.